Okay, for the third video in our little series, I just want to go through the last example in a single-step debugger. So I've opened up RStudio. This is the markdown document. And I'm essentially just going to evaluate each of the chunks as we go. So if you kind of here, and then my next step would be evaluate this function. Okay, so what I'm going to do now is turn on debugging. So I'm going to say debug the superb projection. Now, if I run that function again, it should throw me into the single step debugger. So what I get up here is the source code of the function. And down here, I have a console where I can sort of control the evaluation. So if I sort of just do a single step, so I type N for the next line, and it kind of evaluates these lines as we go. And you can kind of see the values of the variables get displayed up here in this inspector. I think it's reasonably self-explanatory. Our ages is a vector from 0 to 7. Similarly, our spawning interval and our monitoring interval, where it starts to get a bit interesting and a little bit less easy to predict is here. So if we look at ages, I can look at head ages. I can try and look at head ages. No, because I haven't evaluated it yet. Now if I do it. And it basically says, these are the ages. In the first column, we've got sort of the 0th age class, or the first age class, if you want to call it that. Starts at age 0, 1 day old, 2 day old, 3 day old. The first age, starts off at 1 year old, 1 year and 1 day, so on and so forth. If I then evaluate the L's, these are the lengths. This is a von Bertalanffy model. So I can look at that in the same way. I can say head L's, and it says, well, here's the sizes that we'd expect to see. Or alternately, I can plot this. If I plot this against the day of year, days is it? L's, and I'm just going to say type equals L. I get a plot here. Now, the von Bertalanffy model we use here assumes that growth's restricted to this sort of initial part of the year from sort of increment 0 to, fraction 0 to increment 93. So you can see that the growth happens only in this initial stage of the year, and it assumes that they don't change size over the rest of the year. So I can kind of see this against fraction of the year, and here's each of the age classes. They sort of grow, stay constant, grow, stay constant. And if you sort of put these growth sections together, you see you'd get a von Bertalanffy curve. Similarly for the weights, I can sort of go head W's here. I have to say, I don't really understand the units of this. There's some weird unit thing going on that I don't get. These are just, I'm basically just taking the numbers out of the 1996 paper. And there's some weird unit thing. This is either, instead of per recruit, it's something like per 1,000 recruits, or maybe this biomass is measured in, I don't know, individual atoms of carbon or something. But this weight seems incredibly large for a single individual. This should be for the second age class on, day 1, single individual should weigh 105.42.33 something or others. And I can't quite imagine what that is, unless this is done in something like maybe 1,000 or 100,000 individuals. Anyway, perhaps next, we should next look at the matrix of M's. Now, this is the matrix of M's is, and you can see it's 1 to 366. 1 to the number of time steps, remembering that we have one extra because the time steps straddle the days, and there's 1 to 8 age classes. And you see this is just a matrix of ones. Nothing particularly exciting here. We then use this C trap Z function to calculate the cumulative mortality, and this MSF is like the final row of that. So if we look at MSF, it's all 1 because we've sort of scaled the, that's how we've chosen the scaling for the mortality. Similarly, if we look at this FWY, this is meant to be the fishing pattern within year. And if I just plot this against days again, FWY, you kind of see that we don't fish for a little while, we do fish, we don't fish again. So there's a fishing season here in sort of not quite the first quarter of the year. Okay, this is our survey error variability. Again, that's taken from the paper. And then it evaluates this function and it kind of exits at this point, right? So it's done an initial block of computation, but to actually do a projection, we have to call this sim function. So we can debug that as well. Let's go debug sim. And if I then go, sim1, this starts the computation that does a single projection. Okay, so here we've got GS and SS. So GS is sort of determines the maturity. In my mind, GS is kind of gonad, if you want a mnemonic. SS is selectivity. And again, these are matrices. This ramp OGIVE function just basically calculates a ramp. You set the midpoint of the ramp and the width, and it's basing it off the length. We could have based it off the ages or the weights or whatever. It's free for you to do this however you like. But let's have a look at one of these things. Let's look at selectivity. So if we go matplot days SS type equals L. So if you look at this plot, there are some age classes that just are not selected at all. There's one that sort of starts to be selected early in the year, never gets to fully selected because it never grows enough. Then there's the next age class up, starts, sort of is mostly selected, but by, sort of, I don't know, 20% of the way into the year, it's fully selected. And then there's a bunch of age classes that are literally fully selected. We calculate our within our instantaneous fishing mortality by basically combining the season with the selectivity data. So if we plot these Fs, this is our instantaneous fishing mortality. So you can kind of see there were a bunch of things that were fully selected, and now, in the fishing season, they're fully selected, but of course, out of the fishing season, nothing gets taken. Here's that one age class that sort of at the start of the year, wasn't fully selected, gets to 75% selected, and you can just faintly see the next age class up is in there. Okay, let's just progress on. So again, this capital F's is like the cumulative. So let's just plot that and see how that looks. So you kind of see here that for something, the one that wasn't fully selected, it sort of has this slow, sort of almost quadratic growth. The ones that were fully selected, the kind of the cumulative phishing mortality is just this sort of increasing ramp. Okay. And it doesn't, at this point here, the phishing season ends. So whatever the cumulative phishing mortality was to this point, it stays constant because there's no more phishing once the season ends. Next, we pick a natural mortality. So if you look at M.656 something or other, we've just randomly selected a mortality from 0.4 to 1. Again, I've taken these numbers from the original paper, and then we scale that cumulative natural mortality by this M. This thing is the recruitment in the variability, and again, just some numbers taken from a paper. Okay, this creates many recruitment series and then uses those to estimate the median spawning biomass, SSB0. So if you look at that, that's quite a large number. And again, there's some weird unit thing going on that I don't quite grasp, but I've just kind of taken the numbers from the paper. Similarly, we simulate a bunch of recruitments and get an initial age structure. So if you look at N0, that's the initial age structure. Because this recruitment that was used to generate this was chose to have mean 0, you can kind of see the initial numbers are quite low, right? Because it's not mean 0, mean 1. The initial recruitments were meant to have mean 1. They're a little bit variable, so they're up and down a little bit, but they're essentially the initial population abundances we're going to start from. Then if you look at the recruitment series that will be used in the simulation, that's this R. So I think I'll just plot that. Plot R's. So you can kind of see it's varying around. It's essentially a sample from a log normal distribution. The mean should be about 1 because that's mean R's, because that's what we've chosen. It quite close to 1, surprisingly close to 1 actually. And the variability is controlled by this sigma R, which is itself randomly selected. Okay, in the next couple of lines, we just sort of allocate some space to store data. Where it gets really, or starts to get really interesting, is where we do our first real projection. So we're going to use that initial age structure, the mortalities and the weights to project forward. Now there's no phishing here, right? We're assuming no phishing, so none of the phishing stuff enters into it. But we get a sort of an initial projection, and then we set the phishing components and the yield components of that thing to be 0 because, you know, there's no phishing. But if we look at that thing, if we look at, if we look over here, PR0, it says that PR is a list with 4 components. It's got N's, abundances, B's, biomasses, Y is your yield. We've set that to 0, and F is your the scaling of the phishing mortality. And again, we've set that to 0. So then, for example, if we were to plot the biomass PR, well, let's do the abundance as well. PR naught $, N, you kind of see we've got these exponential declines in the biomass over the year with just constant fishing mortality. If we look at the biomasses, they're a little bit more interesting. So here, even though the numbers are declining, there's a sharp rate of growth which is taking the biomass up. So the biomass increases because of the effect of growth, but then declines because of the declining abundance. Given this initial projection, we calculate some initial biomass and we simulate the effect of survey error. Okay, so if you look at the initial biomass for this random projection we've generated, the initial biomass is this 68260. And again, a weird unit I don't quite grasp. So what would happen next is we'd go through, given that as a starting point, we then simulate what happens if you take out a catch. What happens to this population if we remove catch at a particular rate? So I'm just going to step through here. Now, if we look at our gammas, these are the fractions of catch that we're going to consider. And the first one's 0, right? So G is initially 0. That's a kind of a dull one to investigate. So I'm just going to artificially change that to the first one, 0.1, right? And then I'm going to calculate this catch. So the catch is 6826, or 10% of what we thought was there in the monitoring period. So we set our projection back to this initial projection. We calculate a spawning stock biomass based on that. So our SSB is, 50,000 odd. And then we step forward through a bunch of years. Okay, so the first year we skip because we've already done that initial, we're trying to record that initial state, and then we're going to project forward. This recruitment depletion thing, what we're really saying here is if our spawning stock biomass falls below our estimated median spawning stock biomass by a long way, then we're going to reduce recruitment. So if you look at R, at the minute it's 1, because the spawning stock biomass is quite high. So what this advance does is it takes the abundances from the projection for the previous year, uses those, uses the final abundances from that projection to set the abundance for the next projection. Okay, so it uses last year's abundances, the final abundances in the last year, and insert some recruitment. It also does, it also handles a plus group. If your final group's a plus group, it kind of deals with that neatly for you. So it's not a particularly advanced thing. It just does some really basic stuff and sets up our initial abundance for the next year on. Okay, this project C actually projects forward over a year, but tries to ensure that we get the catch we're trying to target. So remember, we're trying to target 10%, which turns out to be 6826.00 something. If we take one step, if we look at PR now, it's a list of 4 items. The abundance, the biomass, the yields in each class, the time, the final yields in each class, and the F that was required to generate these yields. So if we look at, for example, I think we'll just do this. if we look at the abundances, again, exponential decline. If we look at the biomasses, again, we see an initial period of increase in biomass because of the growth, and then there's a sort of a decline as the abundance falls away. If we look at the yields, PR dollar Y, that's the yields per age class. The first two age classes aren't selected at all, so they can't really contribute to the yield. And then, you know, the selectivity starts to increase, and so the later age classes contribute more, but of course they're also dying away, so there's less of them there to contribute. If we look at the sum of that, that's the target catch we were trying to reach. You know, so it's basically selected the F that gives us the target catch. So we store all of this stuff. So we store some basic summaries. You know, what year is it? What fraction of the catch were we trying to pick up? What was the recruitment? What was the sum of the initial abundances? Some of the initial biomasses? A few other things. You know, what's the spawning stock, etc., etc., etc. And slightly oddly, we return the abundances at the start of the year. This is just to be consistent with the generalized yield model. It probably makes a little bit more sense if we return the abundances at the end of the year, but we're just trying to be consistent here. So what happens next? Essentially, we just do the whole process again, right? So we do this for, I think in this case, 20 odd years. You know, we're just going and projecting forward. We advance up the age classes, project again. So if we now look at our plots after, you know, a couple of years have passed, again, exponential decay in the abundance, and our biomasses, again, initial growth, sort of slow decline because our abundance is actually increasing. So this is because they're growing larger. The decline is because they're dying away. And so it would project ahead 20 years, store the results from each year, you know, whatever we've chosen to keep here, but then it goes on to the next gamma in the list. So I don't think I'll try and single step ahead. I'll just sort of talk you through this phase. So having done all of this, 20 years of projection for one gamma, it goes back and says, well, what will our target catch be for the next gamma? Let's reset back to this virgin state, do 20 years of projection again. Then it'll go on to the next gamma, reset back to the virgin state, do 20 years of projection. So in this way, what's actually happening is for the same initial state and the same sequences of recruitments, it's simulating what would happen to the population if we took out none, then 10%, and then I think it's sort of something like 13%. Let's just have a look. Yeah, so none, 10%, 13.6, 15, 20%. If you remove that from the population, what happens in the longer term as you project ahead over 20 years, and what state do you end up in after 20 years? Okay, I think I'll leave that there. But, you know, you're free to do this and experiment as much as you like in your own time. Good luck.